Hey, fabulous calculus students. So this is limits involving infinity, day 2. And just a reminder, we said a horizontal asymptote, by definition, was going to be uh, if the limit as x approached positive or negative infinity for f of x equaled some number. If the limit of a function as x heads to infinity is a number, we're claiming that as a horizontal asymptote. And it doesn't have to be both of these. It could be just a horizontal asymptote going in only one direction. We also said vertical asymptotes were defined this way. Limit as x approaches some number of f of x equals plus or minus infinity. So as I approach an x value on the graph, if the function is heading to infinity or negative infinity, that's a vertical asymptote for us, okay? And remember that the limit as x heads to 0 of sine x over x, or the limit as x heads to 0 of x over sine x, these are 1, but the limit as x heads to infinity of sine x over x is not the same, nor is the limit as x heads to infinity of x over sine x. So you should make sure that you know these from the last video um, before you take a test on this unit. Okay, so I want to take a minute now because we're about to get into a conversation um, about some physicsy things, um, and I want to just clearly define some things. Okay, so if I have a position function, I plug in time and I get out position. By the way, sometimes position is written as s of t, position as a function of time. But this is also a way to describe position as a function of time, x of t. Okay, so you need to be comfortable with both of those being position. Now, if I have a position function and I want to talk about um, the rate of change in position with respect to time. So it's a change in position over a change in time. When we're talking about a change in position with respect to a change in time, that's how we define velocity. Not speed. Speed's a different thing. Velocity. Velocity is a change in position with respect to time. So when we talk about, when we talked about the microscope worksheet, we said that we could approximate the slope at a point using the microscope technique of wicked close points in the slope formula. If we did that technique of trying to graph that f prime, that slopes graph, well, if we did that technique on a position function, the prime that we'd be graphing is a velocity function. So here's what I'm trying to say. If s of t is this parabola, okay, position with respect to time. Here's time, here's position, and this is my graph of I put in a time and I get out of position. Great. But if I want to talk about the rate of change in position with respect to time, I can do it in one of two ways. And we've seen this already. I can talk about the average rate of change, And when I talk about the average rate of change in position with respect to time, what I'm finding there is average velocity. And the way I do that is I simply find the slope between those 2 points. Okay, so equals slope. Now I need more space, clearly. So average rate of change is slope between 2 points on a graph. So if I want average velocity, that's going to be the average rate of change in position. It's the slope on the position graph all right, that's what my average velocity is. It's the average rate of change of position with respect to time, and so it's the slope on the position graph between 2 points. And so all I have to do is find that by doing S of B minus S of A over B minus A. Finding the slope, S position on the position graph between 2 points, A to B. Okay? Now, we've also got instantaneous rate of change. And we understand that to be slope at a point. And we're still struggling to come up with a way to actually find the slope at a point. Right now, the best we can do is like we did on the microscope worksheet, where we use 2 points that are wicked close together on that curve to approximate the slope at that point. Our approximations can be really good, but they're still, we have to acknowledge that they are approximations. Okay, if I want to talk about instantaneous velocity, then that's going to be the rate of change in position with respect to time at 1 point. Okay, so this is only at x equals a. And yeah, so that's a little more problematic for us to find right now. I can also understand it as the slope at a point on position. Okay. Speed. Let's talk about speed. If S prime, that's the graph of all the slopes on ST, if that is this, then what's speed? Well, speed is the absolute value of velocity. And we'll be talking a bunch about, well, we'll be talking a bunch about all these terms all year long. So don't worry if you're feeling a little uncomfortable with all this knowledge. I will say the sooner you can understand that the slopes on position give me velocity, and the slope between 2 points on position gives me average velocity, and the slope at a point on position gives me instantaneous velocity, I think the happier you'll be. But I do understand that it's a bunch to learn. Okay, so then I want to say speed is the absolute value of velocity. that's a sort of side special thing. And then I want to mention this term, acceleration. Um, Acceleration turns out to be the rate of change in velocity with respect to time. And so I could think about acceleration as a change in velocity with respect to a change in time. That also means that the slopes on velocity are acceleration. And since velocity is the slopes on position, then we could actually define acceleration to be the rate of change in the rate of change, no, it really is that, in position with respect to time. The rate of change in the rate of change in position with respect to time. I know velocity is the rate of change in position with respect to time. I know acceleration is the rate of change in velocity with respect to time. But since velocity is the rate of change in position with respect to time, then acceleration is the rate of change in that rate of change of position with respect to time. And because that's a lot of words to say all the time, we say this. We say S is position. We say the rate of change or slopes on S is going to be velocity. And then we could say S double prime equals V prime equals A of t, and that's acceleration. Okay? So this notation means the rate of change in the rate of change in position with respect to time. This is the rate of change in velocity with respect to time. So acceleration can be defined in either of these ways. And just like we had average velocity and instantaneous velocity, so too we can have average acceleration is going to be the slope between 2 points on velocity. Okay? Instantaneous acceleration is going to be the slope at a point on velocity. Okay, so that's a whole lot of vocabulary for us. But like I said, we're going to be doing an awful lot with this vocabulary. So it's good for us to start to get it. And while it's not in tonight's homework, it's coming soon, and I thought we should certainly touch on it in a gentle way um, before we before we went too much further. Okay, let's move on to our conversation about um, limits involving infinity. Um, how about you tell me, based on yesterday, a little bell work, the limit as x heads to infinity of 3 plus 7 over x. Okay, please find the value of that limit. Well, welcome back. You know, for me, I always think about splitting these things up using our limit properties. And so if I try to plug infinity in there, well, that's awkward. But if I think about it with the pizza metaphor, 7 pizzas and an infinite number of people show up, I know that's 0. The limit of a constant as x heads to infinity is that constant. And this is that horizontal asymptote definition that we talked about before. And so we know this limit is equal to 3. Okay. How about this one? The limit as x heads to negative infinity of x squared. Now, I like to think you can know this graphically, right? Oh, here's x squared. Here's as x heads to infinity, where's the function going? The function is going to infinity. But I know that I can also think about this as the limit as x heads to negative infinity of x times the limit as x heads to negative infinity of x. And some people want to be thinking about this as negative infinity times negative infinity, and therefore a negative times a negative is positive infinity. Uh, I find it nice when math can have internal consistencies like that. All right, so next. Um, do you remember in Algebra 2 and in pre-calc when we had a rational function like 1 over x or like 1 over 2x plus 1 over 3x minus 5 or y equals x squared over x plus 2? In each of these cases, we had to figure out horizontal asymptotes, remember? Okay, so we now know that a horizontal asymptote is the limit as x heads to positive or negative infinity of that function. So we're going to come back and have this conversation about these horizontal asymptote options. So let's think about that. Where was the horizontal asymptote when the degree on top was smaller than the degree on the bottom? That was at y equals 0. Okay. Where was the asymptote when the degrees were the same? Oh, we said the ratio of leading coefficients. And here we said, oh, there's not a horizontal asymptote, there's a slant asymptote. Because the degree of the top is bigger than the degree on the bottom. And that works really well, except now I kind of want to do this different because we're going to be thinking in terms of limits and we're going to be thinking about what we're approaching. So instead, I want to have a conversation about end behavior models. And end behavior models are essentially describing how a function behaves as x heads to infinity or x heads to negative infinity. And some of them we already know. We know, for example, that when we see y equals 1 over x, we know that y equals 0 is the end behavior model. And we know that because the limit as x heads to infinity of 1 over x equals the limit as x heads to negative infinity of 1 over x, and both of those limits are equal to 0. Okay? So y equals 0 is the end behavior model. Now, in our class, it's calculus, and it's not pre-cal or algebra 2. So when I'm asked to say, hey, what's the limit as x heads to infinity of 2x plus 3 over 5x plus 7, I'm not allowed to say 2/5 like that. That's considered a bald answer. And I don't have any evidence. There's no work shown. So now, because we're going to have to, show some sort of calculus, some sort of relationship evaluating this limit, what I'm going to say is that I want to multiply top and bottom by 1 over x, because these are x's. Now, if these were x squareds, I'd be doing 1 over x squared. Okay? We'll do that one next. So, if I multiply over here by 1 over x and here by 1 over x, and then I distribute, what do I get? Well, I'm going to have the limit as x approaches infinity of 2x over x plus 3 over x over 5x over x plus 7 over x. Now I can definitely simplify here. And so now I'm thinking about the limit as x heads to infinity of 2 plus 3 over x. I could even split it up and say the limit as x heads to infinity of 5 plus 7 over x. Now, let's think about this limit up here in the numerator. If I plug the infinity in there, 3 pizzas, an infinite number of people, what happens to that? That's right, that becomes 0. So I've now got the limit as x heads to infinity of 2 plus 0. Actually, once I plug that infinity in my head, I don't need to show that limit notation anymore. And on the bottom, if I put my infinity in here, 7 pizzas divided by an infinite number of people, and so we end up with 2/5. Y equals 2/5 is our end behavior model because because 2/5 is the value of this limit. But I'm not allowed to say the leading coefficients are 2 over 5, therefore y equals 2 over 5 is my end behavior model. I'm not allowed to do that. I have to show some manipulation of that limit in order to earn that point, okay? So let's extend that idea. Let's go further and say, all right, well, what about this one? The limit as x heads to infinity of 5x squared plus 7x over 3x plus 2. So again, I want to get rid of this. So I multiply by 1 over x squared on top and bottom. When I do that, I'm now going to have the limit as x heads to infinity of 5x squared over x squared plus 7x over x squared over the limit as x heads to infinity of 3x over x squared plus 2 over x squared. So is there any simplifying we can do here? Sure, we can cancel these out. We can take this one with one of those, this one with one of those, and no canceling here. So now I'm looking at the limit as x heads to infinity of 5 plus 7 over x. And then on the bottom, we've got 3 over x plus 2 over x squared. Okay, so what's that getting me? Well, let's have some more space. When I try and plug the infinity in, that's going to be 7 over infinity. So a finite number of pizzas, an infinite number of people. That's going to be 5 plus 0. But what about on the bottom? Well, on the bottom, when I plug these in, I'm getting 3 over infinity, which is 0. I'm getting 2 over infinity squared, which is 0. And so I'm getting 5 over 0. Okay, what's that mean? Well, we used to say that's undefined. Now, I think we should say that's going to be infinity, or is it negative infinity? So let's think about this. Let's think about this. When we were in Algebra 2 and Pre-Calc, we said if the degree on top is bigger than the degree on the bottom, we'd have a slant asymptote, and we could find that by doing some long division. Oops, 7x. So how many times, what do I have to multiply this by to turn it into that? I have to multiply it by 5/3 x. Because then the 3 will go away, and the 5 will show up, and x times x makes x squared. So I've got 5 x squared plus 10/3 x. And then I would subtract, and I would get 21/3 minus 10/3 is 11/3 x. And what would I multiply this by to turn it into that? Well, I think I'm going to multiply that by a 9 here and an 11 here. Okay, and so that would be my slant asymptote. But I actually want to ask a different question. While it's true, I could say y equals 5/3 x plus 11/9 is the slant asymptote. It's n, therefore, it's also my end behavior model. I also want to think in terms of this limit. So when I did that dividing, I had 5/3 x plus 11/9 plus 11/9. Where's this function headed? What does this function look like? So the limit as x heads to infinity follows this slant asymptote. The function, this function, as x heads to infinity is headed where? Well, it's headed up. It's headed towards infinity. Whereas if I had the limit as x approaches negative infinity for 5x squared plus 7x over 3x plus 2, where's that headed? Well, that's going to be headed down to negative infinity. So I guess I kind of want to be talking about two things here. I want to be talking about where is the function headed, and I want to be talking about end behavior models. And an end behavior model describes how I get where I'm going. Okay, so I know that the limit as x heads to infinity of 5x squared plus 7x over 3x plus 2, when I multiply by 1 over x squared and 1 over x squared, I'm going to have the limit as x heads to infinity of 5 plus 7 over x over 3 over x plus 2 over x squared. And then when I plug my infinities in, that gives me 5 plus 0 over 0 plus 0, which is 5 over 0. And I'm not going to say undefined. I'm going to say, where is this function headed? Well, we know this function is headed up that way because we already found the slant asymptote. So instead of saying undefined, we're going to say this is headed towards infinity. As opposed to, if we put a minus here, and I plug in my negative infinities everywhere, 7 divided by negative infinity, 3 divided by negative infinity, that doesn't seem to change, does it? We still end up with this. But because I'm headed in the other direction, I know that this thing has that slant asymptote, that end behavior model of 5/3 x plus 11/9. When I think about where this function is headed, I know that I'm headed down forever, and therefore that this limit is equal to negative infinity. So often I find I have to think about these questions carefully. Where I'm headed is the value of my limit. The end behavior model is how I get there. I would like to say this though. I think it's okay for us now to talk about end behavior models for polynomials in perhaps a gentler way. So, for example, if I have y equals 3x to the fourth minus 2x to the third plus 7x squared plus 4x minus 2, and I'm asked, hey, what's the limit as x heads to infinity for this function? I'm going to say that is infinity. And how do I know that? Well, because I know the end behavior for a fourth degree polynomial with a positive leading coefficient. Both ends go up. All of this stuff, yeah, it's just like squiggly in the middle. But if we're talking about limit involving infinity, 3x to the fourth wins. I mean, this guy can complain all he wants to say, no, let's go down. 3x to the fourth is going to say, woo, we're going up, because this function grows so much faster than this one, okay? So what I'm getting at here is I can know with any polynomial the limit as x heads to infinity or negative infinity just by knowing the degree and positive or negative leading coefficient. In fact, we can say the end behavior model for any polynomial will be the first term if we're in standard form. And by standard form, I mean descending order. So that's my end behavior model. f of x equals 3x to the fourth is my end behavior model for this polynomial. I mean, if I think about plugging in infinities, infinity is really big. It's really, really big. So let's just plug in something that's not really, really big, like 1,000. So 4 times 1,000. Wow, that's so much bigger than 2. So the 2 doesn't really play a role. 1,000 squared is so much bigger than just 1,000 that we really don't have to worry about that. And yet over here, if I put in 1,000 and I cube it, there's so many zeros. Poor x squared with its 1,000 squared feels like I can't compete. And that's exactly what happens over here. 3x to the fourth is just so dominant that negative 2x to the third slinks away. And we say, look, it may have behaved in lots of different ways in the middle of the graph. But really, if we're talking about an end behavior model, if we're talking about what this thing does as x heads to infinity or as x heads to negative infinity, it's always going to be the highest power. And that's kind of very reassuring. In fact, I think we could even say, do I want to say that or do I not? I don't want to say that. Yeah, I'm not going to say that. So instead, I'm going to say, hey, let's find f of x equals x squared plus x minus 6 over x squared minus 4. Let's see what we can do about describing vertical asymptotes, horizontal asymptotes, and end, I guess that's end behavior models. Okay, so let's think about this. Well, I know for end behavior models, I want to think about the limit as x heads to infinity of f of x. And so I'm thinking about x squared plus x minus 6 over x squared minus 4. Okay? And I'm thinking that I want to multiply top and bottom by 1 over x squared. And so now I'm going to have the limit as x heads to infinity of x squared divided by x squared is 1 plus 1 over x minus 6 over x squared over x squared divided by x squared is 1 minus 4 over x. So what happens when I plug infinity in here? Well, I get 1 over 1, which is 1. So I know that not only is this limit equal to 1, but I could say my end behavior model in this situation is going to be y equals 1. And that's very reassuring to me because I remember learning in Algebra 2 that when the degrees were the same on top and bottom, I look at the ratio of leading coefficients, and that's that 1 over 1, or 1. I just now have a way of showing that with my limits that is the end behavior model because that is the horizontal asymptote. Okay, now what about vertical asymptotes here? We remember from the beginning of this video that a vertical asymptote is the limit as x approaches some number of f of x equals plus or minus infinity. So do we have any places like that here? Any places? Well, I remember in Algebra 2 and in Pre-Cal, we talked about, in fact, we started this year with the benefit to factoring these rational functions. What does it mean when I cancel these out? Well, it means that there's a hole at x equals 2. There's a hole at x equals 2. Is that an asymptote? No, that's not. In fact, if I want to know the limit as x heads towards 2 of f of x, I can take that 2. If I plug it into here, I end up with 0 over 0. But if I rewrite this and cancel out those factors, I could now plug in my 2 here and here, and I end up with 5/4. The point doesn't exist, but the y value of the whole would be 5/4. Okay? But that's not a vertical asymptote, and we were asked to find vertical asymptotes. So what do I have for a vertical asymptote? Well, when I take these away that make the whole, I now have this. And if I consider the limit as x heads to, say, -2, x plus 3 over x plus 2, what happens if I plug a -2 in here? Well, I get 1 over 0. Aha! That is infinity. Or is it negative infinity? Let's think about this graph. Let's think about this. Is the limit going to be the same whether I come from the positive side or the negative side? And I think we remember enough of graphing rationals to be able to quickly graph this and answer that question. We have an x-intercept at -3. We have a vertical asymptote at -2. At 3/2, we have a y-intercept. And here, horizontal asymptote, we found y equals 1. So what do I know? Well, I know that as x approaches -2 from the positive side, I am headed to infinity. And if I'm considering instead the limit as x heads to -2 from the negative side of this function, well, as I approach to -2 from the negative side, that limit is negative infinity. Now, I don't feel like I know that from this. Like, what's the difference between plugging the -2 in from the positive side versus the negative side with this, like from an algebraic point of view? For me, it's always, I have to think about this graphically or think about a table in order to know what the distinction in these limits will be. And if I know the graphs, it's very easy for me to say, this function, as x heads to -2 from the negative side, is going that way. Okay, so I want to say, simply, because the limit as x approaches to -2, from the positive side equals infinity, therefore, oh, by the way, you could write this. This symbol means therefore. Therefore, there is a vertical asymptote at x equals -2. Okay? Simply stating this is sufficient. I don't have to do both sides. I can only do one side, and I would still have always a vertical asymptote there. You could certainly be, a completionist and want to say the limit as x approaches -2 from the negative side heads to negative infinity, and have them both down. That's certainly more robust, but you only really need one of them. Okay, wow. So this is a little more intense than the way we dealt with asymptotes in pre-cal. But that doesn't mean that you're not up to it. So here's an f of x, negative 3x squared plus 2 over negative 6x squared minus 2x plus 5. So um, tell me what is the limit as x heads to infinity of f of x in this case? Pause the video, give this one a try, see where it takes you. Welcome back. So I'm looking for the limit of f of x as x heads to infinity, negative 3x squared plus 2 over negative 6x squared minus 2x plus 5. And this is where I need to show that I'm going to multiply top and bottom by 1 over the highest degree x. So when I do that, what do I get? Well, I'm going to get the limit as x heads to infinity of negative 3 plus 2 over x squared over negative 6 minus 2 over x plus 5 over x squared. Okay, well, let's think about what happens when we plug an infinity in here. If I plug infinity in here, in here, in here, those all turn into zeros. And so now I'm looking at negative 3 plus 0 over negative 6 plus 0 plus 0. I guess to be consistent with the notation, I should use a minus there. So this is negative 3 over negative 6, which is 1/2. So I know that y equals 1/2 is my end behavior model. But I also know that the value of this limit is 1/2. Okay, so that's my horizontal asymptote at y equals 1/2. Now, do I have any vertical asymptotes to think about here? Well, let's take a look at this denominator. Do we have any place where this denominator is undefined? Well, I'm not actually sure that I can find the factors of negative 30 that add up to negative 2. So I'm not sure that this is going to be factorable. So let's see. Negative 130, negative 215, negative 310, negative 5, 6. Those are the factors. Well, and of course these could be negative, but no, that's going to be 1, and that's going to be 7. I could get negative 6 and 5, negative 1, or I could get negative 7, but I don't have anything in between. So I'm not actually going to be able to factor this. I wonder what I could do to find zeros of this function, because that's what I'm really concerned about, right? When the denominator is equal to 0, then I'm thinking I have a vertical asymptote there, unless I have a hole. So how about this? X equals negative b plus or minus square root b squared minus 4ac all over 2a. So we've got 2 plus and minus square root 30 times 4 is 120 plus 4, 124 over negative 12. All right, so these are zeros of this function. And if these are zeros of the function, well, guess what? Those are probably vertical asymptotes unless I have them up here as well. So where are the zeros here? Well, 3x squared plus 2 equals 0. 3x squared equals 2. X squared equals 2 over 3. So x equals plus and minus root 2/3 u, which is plus and minus root 6 over 3. Well, that is not that. So I know that I'm not going to have any factors on top canceling with the factors on the bottom. So those are going to be where my vertical asymptotes are. Ew. So do I know how this function behaves near those points? No, not really. And this is why I say I often want to turn my attention to a graph to understand Well, what is the limit as x approaches 2 plus square root of 124 over negative 12 from the negative side or the positive side? I think thinking graphically about that could be very, very helpful. Um, so I would say graph that one. Let's graph it on our calculator. Okay, and now I've got parentheses negative 3x squared plus 2 on top divided by negative 6x squared minus 2x plus 5 on the bottom. And sorry, I was in such a rush. So we had 2 plus or minus square root 124 over negative 12. And that's 31 times 4. So I guess I could do 2 plus and minus 2 root 31 over negative 12. Factor out a 2. And so I could cancel and get negative 6. So let's take a look at negative 1. Let's take, yes. No. 1 plus root 31 over negative 6, and 1 minus root 31 over negative 6. So these values, okay, 1 plus square root of 31 divided by negative 6, this is negative 1.094627,394. And this one, 1 minus square root of 31 divided by negative 6, I get positive 0.7612940605. Okay, so what I want to think about is this thing that I plugged in here, how does it behave near these x values? So I'm going to make my window pretty small. I'm going to go negative 1.5 to positive 1 in steps of 0.1. Yeah, and how about negative 2 to 2? Let's see what that does. Oops, graph. All right, so that's a good enough viewing window for me to say, hey, I've got vertical asymptotes. I have vertical asymptote at x equals 1 plus root 31 over negative 6, because the limit as x heads to 1 plus root 31 over negative 6 of f of x from the positive side equals negative infinity. And I know that there's another vertical asymptote at x equals 1 minus root 31 over negative 6. That's this one, because the limit as x heads to 1 minus root 31 over negative 6 from the negative side, this limit of f of x is equal to infinity. As I approach x equals this 0.761294 number, f of x is headed up to infinity. Okay. No, I don't think you're going to have anything this hard on a test for me or even on the AP exam, but if I can get you comfortable with horrible things, you'll be very comfortable when it's a little less horrible, like the AP exam. All right, so the last thing I sort of want to touch base with you on is I want to give you a permission. Remember how we said with f of x equals 3x to the fourth plus all those other things, that our end behavior model was just going to be this and we were going to ignore all that? Well, so now I want to come back to rational functions. If I have a rational function, minus 5x minus 8 over x plus 6, and remember in Algebra 2 and Pre-Cal we said if we wanted to find the slant asymptote, we would have to divide this into this. I even showed you an example of that a little earlier in the video. Well, no, I don't really want to do that now. In fact, I want to say, look, the limit as x heads to infinity of f of x, as these values head towards infinity, that doesn't play any role. That doesn't play any role. In fact, because I'm looking at infinity squared, yeah, sorry. So here's what we're going to do now. We're going to say, if you want a quick end behavior model, then you look at this, and you say, that's the limit as x heads to infinity of x squared over x, which is the limit as x heads to infinity of x. And you know the graph y equals x heads that way. So you say infinity. Okay? So this is my end behavior model. And you say this is the value of the limit. Now, because one or two of you out there may be really paying attention really closely, you may recall that I said in our first limit video that a limit is a number. And infinity is not a number. Infinity is, in fact, a destination. It's not a number. And so in 2.1, we are uncomfortable saying, okay, the limit is x heads to infinity of x squared. We want to say this in 2.1. We want to say this is undefined because when I plug infinity in there and square it, I don't get a number. And a limit is supposed to be a number, so I say that limit is undefined. But by the time we get to 2.2, we're now understanding this limit as x heads to infinity as where am I headed? And so if you were one of the few people who was really concerned about, well, a limit is supposed to be a number and infinity is not a number, you're going to have to let go of it a little bit and just understand that, yeah, we're going to say that this limit is equal to infinity because I'm thinking about this limit as explaining where am I headed? Where does this function go as x heads to infinity? Well, it goes up to infinity. That's going to be a much more useful answer than, yeah, I don't know, shrugs shoulders, okay? All right, so um, last problem. F of x equals 2x to the third minus 3x squared plus 1 over x plus 1. And I want to say, hey, what's the end behavior model? Okay, well, I can approach this in a couple of ways. I can certainly do 1 over x to the third over 1 over x to the third. And that can tell me the value of the limit to a degree, right? Because I'm going to have the limit as x heads to infinity of 2 minus 3 over x plus 1 over x to the third over 1 over x squared plus 1 over x to the third. And here I get 2 over 0. And so I want to say, is that infinity? Oh, but wait, maybe it's negative infinity. So I can use this approach to try and evaluate the limit, but sometimes the end behavior model is actually more helpful in that, right? So let's think about our end behavior model. Our end behavior model, 2x to the third over x, is 2x squared. And so if you ask me, hey, where does this end behavior model go as x heads to infinity? Limit as x heads to infinity of 2x squared. Well, I'll say both ends go up. So I know that, whereas when I look at this 2 over 0 thing that I get by using this approach, I don't know if that's infinity or negative infinity. There's nothing here that tells me that. Okay, so an end behavior model can actually be helpful. Find it first to help you then understand what this means. Because I have this 2x squared, I know that when I get this limit value, that my function is really following y equals 2x squared, and therefore this limit is infinity. Now, if I had a negative here, and this was negative 2x squared, I'd have negative 2 over 0, but I still wouldn't feel like I'd know whether this was infinity or not. But because I know the end behavior model has both ends going down, then I do know this. Okay? I'm not comfortable saying because this is minus, this is minus, or because this is plus, this will be plus. But I am comfortable saying you can confirm reality with your end behavior model. Okay, wow, that was a lot of thinking. So here's what I want to say. I want to say that evaluating limits starts off really easy with direct substitution, but then sort of winds its way into troubling waters where we have these infinities to deal with. And really, it's not the limit that's causing you stress and anxiety, it's the infinity that's causing you stress and anxiety. Infinity does that because it isn't a number, it's a concept, it's a destination. It's that I'm I'm gonna make a pilgrimage to Mecca at some point in my life. But yeah, that's also maybe I will, maybe I won't. But it's a goal, it's a destination, it's a direction to head. And infinity, unlike making the Hajj, is probably something I can never. Well, I know it's something I'll never ever get to. There might be a chance of me making a Hajj, but there's no chance of me having lunch with you at infinity this afternoon. Okay, so I can't wait to hear your questions. Oh, sorry. Yeah, I just flipped over and I noticed that there was one more set of end behavior things to talk about. Okay, so let's imagine that instead of a polynomial function, because with a polynomial function, I know that's my end behavior model, and instead of a rational function, where I look at that for my end behavior model, what if I've got this function? I mean, these are so nice and easy. What, what if I have this function equals e to the x minus 2x? And I want to claim an end behavior model here. Well, um, grr, I don't know how they play together. I know this, though. I know if I think about the limit as x heading to infinity for f of x, I know that this function is exponential, and this function is going whee up to infinity wicked fast. But at the same time, this is headed towards negative infinity. So, how do we know where we go? And so an end behavior model is called for. And we may not have the same end behavior model as we head to as x heads to infinity versus as x heads to negative infinity. Have you ever been in a long car ride with your parents? I mean, a long car ride. I don't mean up to Phoenix. I mean like you're in the car all day kind of car ride. I've been in lots of those car rides with my wife, and one of the things becomes very clear. There's always a dominant personality, and it may be the same person as the dominant personality for the trip there and the trip home. It may be that there's a different dominant personality for each of those trips. So I will say that on the way to family Christmas in Colorado with my wife's family, my wife would always be of a mind that we should make as many stops as humanly possible. I mean, if there's another place to go pee, we should stop there and pee and see what the gift shop has. And that would drive me insane because I just want to drive straight through and only stop when the car runs out of gas. Okay, clearly we have two different directions or two different ways we want to approach this trip. And so if I think of the limit as f of x heading towards infinity, at the limit as x heads to infinity of f of x, I can think about that trip to Colorado where we've got two dominant personalities who both want the trip to be a different way. And you know the car is going to follow one of those personalities. Well, it turns out on the way there, it's always my wife's personality. And on the way home, it's always my personality because even by then, she's eager to get home too. So, what does that mean here? What is this silly metaphor he's giving me? Well, what I want to say is the end behavior model for this f of x is going to be one of these. It's just always going to be Kukla or Kukla's wife, or Kukla or Kukla's wife. It's going to be one of these pieces of f of x is going to dominate. And it may not be the same piece in both directions. So let's think about this. Let's think about the limit as x heads to infinity of e to the x minus 2x. And I want to know an end behavior model for this. And if, I could do this in a couple of ways. If I can figure out the value of this limit, if this limit is headed towards infinity, then I know that one's working. If this limit is headed towards negative infinity, sorry exponential, this one says I'm headed to negative infinity. And so I could kind of do it that way because I know the graphs of these pieces. But that won't always be obvious. And so what I want to suggest to you is that we do this. We pick one of them. Let's pick one of them to say, where are we going? How's this going to work out? Okay? So I'm going to say, I think e to the x is going to dominate. And so you put the 1 you think is going to dominate in the denominator. Now, how does this help me? Well, I use my limit properties and break this fraction up like this. So now I've got 1. Now I've got the limit as x heads to infinity of 1 minus 2x over e to the x. Okay, so what's happening here? Well, I'm a little uncomfortable about this because really I want to say that's infinity over infinity, which is, we know, an indeterminate form. And while I've promised you a technique at the beginning of March to help you deal with indeterminate forms, this isn't March. And so what I want you to think about here is if I plug in 100, this is going to be negative 200, but this is going to be e to the 100 power. Now, I'm interested to know if I type in e to the 100, if my calculator will say that's too big a number. No, but it is 10 to the 43rd power, right? So negative 200 can't compete with 2 times 10 to the 43rd. So this is heading to its infinity way faster than this one. And because of that, this is going to be 1 minus a number over infinity, which we know is 0, and so this limit is 1. Now, because I get 1 here, that tells me, yay, you chose correctly. And that means that the end behavior model as x heads to infinity is e to the x. But what about as x heads to negative infinity? Okay, let's think about that. Or did you want me to try guessing the other one? All right, let's guess the other one. See what happens if we put the minus 2x here. So now I have the limit as x heads to infinity, e to the x minus over negative 2x plus 2x over 2x. Okay, so what does that give me? Oh yeah, that's a negative divided by negative. Is that positive? Well, that now gives me the limit as x heads to infinity of e to the x over negative 2x plus 1. Well, now what happens when I plug infinity in? If I plug infinity in, I have e to the infinity over negative 2 times infinity. And you say, well, that's infinity over infinity. I don't know what that is. Yes, but let's not put infinity in. Let's only put 100 in. This is 10 to the 43rd, and this is negative 200. So I'm sorry, this thing is blasting up to infinity. And so what this is really, effectively, is infinity plus 1. Infinity plus 1 is not 1. I did not guess correct. This is not my end behavior model as x heads towards infinity. Okay? All right. So let's go in the other direction. The limit as x heads to negative infinity of e to the x minus 2x. Now, if we plug in negative infinity here, this is 1 over e to the infinity, which is 1 over infinity, which I could say is 0. This function is headed to 0. But what about this piece? Well, if I think about the graph of negative 2x, as x heads to negative infinity, this graph is headed up to positive infinity. So, these parents, they want to head in two opposite directions. This one says, I want to head to 0. This one says, I want to head to infinity. Which function is going to win? Well, I got to pick one. So let's pick one. Okay, the limit as x heads to negative infinity of e to the x minus 2x over minus 2x. Okay, so let's see. That's going to be the limit as x heads to negative infinity of e to the x over negative 2x plus 2x over 2x. And I know that's going to be the limit as x heads to negative infinity of e to the x over negative 2x plus 1. All right, now, if I plug a negative infinity in here, that's e to the negative infinity over negative 2, negative infinity. What happens with this? Well, I can flip that down to make it e to the positive infinity times 2 times infinity. Well, look at that. One pizza and all these people coming to dinner. That is 0. And so what I've got now then is 0 plus 1, and that's 1, and therefore we guessed correctly. Y equals negative 2x is our end behavior model as x heads to negative infinity. So, yeah, there you go. End behavior models. Woohoo! That's what limits involving infinity can help me find, is end behavior models. And you'll actually need end behavior models a lot in Calc 2. This year, we're doing just Calc 1. So after this, we're going to just let it aside for a long time, and we'll come back to it in March. All right, I hope you have a great day, everyone. Let me know if you have questions. Bye.